Hello everyone. The title of my presentation is Reliable Community Search on Uncertain Graphs. Community search is an emerging topic in data engineering. Given a graph G, the community of a query vertex Q is a vertex subset, which has four requirements. First, it contains the query vertex Q. Second, the minimum degree of the induced subgraph is not less than k, which means it is a k-core. Third, it is connected in the subgraph. Finally, it is the maximum vertex subset that satisfies the above three requirements. Figure 1 shows an example. It is called a k-community of Q. K-community use k-core in the definition. Besides k-core, the literature also shows other commonly used metrics, such as k-trust and k-click. Community search has rich applications. Recommendation on social networks and protein complex identification on PPI networks are two examples. On the other hand, uncertain graph is a special type of graph structure where edges are uncertain to exist. There is a probability function p mapping each edge to its existence probability. Figure 2 shows an example uncertain graph. A popular concept to understand the uncertain graphs is the possible world semantic. We assume all the edges are independent. Therefore, a single uncertain graph has exponential number of possible structures. We call each of the possible structures a possible world. One possible world of the uncertain graph in Figure 2 is displayed in Figure 3. With the independence of the edges, we can calculate the existence probability of each possible world directly. For applications, lots of networks can be modeled as uncertain graphs, such as social networks, PPI networks, citation networks, etc. Previous studies on community search start from the undirected and simple graphs. Some efficient techniques were proposed, like the global and the local search algorithms. In view of the large graph size in real applications, recently, some work tries to address the community search problem with size constraint. Besides, community search on complex graphs is also an emerging topic. Related graph types include attributed graph, temporal graph, heterogeneous graph, etc. Usually, there are new challenges when it comes to different types of graphs because of the different structures and characteristics. On the other hand, some studies have proposed the probabilistic dense subgraph models for uncertain graphs. These models are designed to analyze the entire graph, so they usually have no query vertex and cannot adapt to the community search problem. To our knowledge, no previous studies focus on the community search problem on uncertain graphs. We found this new problem meaningful and have broad applications. One of the motivation examples is friend recommendation. Suppose we have a social network. Given a query vertex Q, which means a user, we can find Q's community, and then recommend new friends to Q from the community. However, the K community introduced in the background is usually too large on a large social network. It's still hard to ensure the quality of the recommendation if there are so many candidates. Some recent work tries to address this problem by limiting the size of the community. For example, in Figure 5, the minimum k-core returns the community with minimum size. However, as it is shown, the minimum k-core sometimes is not unique. The definition cannot tell us which one to choose, which causes the result has poor interpretability. In this work, we utilize the probability information to narrow the result size and give users the most reliable friends. So, in the following, we come to the definition of k-theta community on uncertain graphs. Given the edge probabilities, we want to model how reliable of each community member by attaching a confidence value to each vertex. As shown in Figure 7, after this process, those vertices with higher confidence values are more reliable for the query vertex. Formally, we define the k-theta community as follows. Given an uncertain graph, wrote as the swatch letter G, a query vertex Q, and parameters k and theta, find a vertex subset where all the confidence values are greater than or equal to theta. In the formula, all the possible words are considered. For each possible word, if the vertex belongs to Q's k-community, its confidence value is increased by the probability of the possible word. We prove that the problem is NP-hard, which means that it has no linear exact solutions. We design an efficient pipeline to solve the problem. First, for an input uncertain graph dataset, we build the core decomposition index at the offline phase. Then, the users input the query vertex and parameters for community search. We present two effective pruning strategies in the system, namely graph structure pruning and necessary condition pruning. After the pruning step, the original graph and the candidate set has been reduced to a small set. Next, we propose 3 sampling techniques as alternatives to do the remaining jobs. The sampling procedure is used to approximate the confidence values defined in the k-theta community. Finally, the system will output the k-theta community members for the query vertex. Let's go through each component in the pipeline. First, the core decomposition index, namely CD index, starts the k-core decomposition of the uncertain graph for each possible k. The example is shown in Figure 8. With CD index, the k-community of each vertex can be fetched in constant time. The optimizations of the index construction are omitted here. The pruning strategies, graph structure pruning and necessary condition pruning, are used to shrink the size of graph structure and candidate set. Specifically, in GSP, we prove that for each k, the k-theta community must be a subset of the k community. Therefore, vertices outside the k community can be dropped safely. In NCP, we only use partial requirements of the k-theta community definition to get a smaller candidate set. For example, C1 represents vertices with degree larger than or equal to k, and C2 only requires vertices connected to the query vertex. Only if C1 or C2 cannot form a community, both of them neither. Figure 9 shows an example where both C1 and C2 are satisfied, but the result set is not a community. Therefore, the probability of the intersection of C1 and C2 gives an upper bound of the true confidence value. In the pruning step, although we haven't calculated the expensive confidence value, we have cut most unqualified vertices. The final step is to sample the graph and approximate the confidence value. Recall the formula in the definition of k-theta community. We find that it needs to visit all the possible words. In most scenarios, it is too expensive. Therefore, we resort to sampling techniques. The basic choice is the Monte Carlo sampling. It simply samples n possible words from the uncertain graph, where n is a hyperparameter. Then, the search space is reduced from the exponential number to n. However, Monte Carlo sampling may bring large variance due to its totally random sampling process. We present the stratified sampling technique to control the sampling process. It has 3 steps as shown in the figure. First, we pick out R edges from the graph, where R is a hyperparameter. A stratification design table is formed based on the R edges. Specifically, we divide the sampling space to R+1 groups. In each group, we set some edges to exist or not, and leave the other edges to sample. Different groups are disjoint cases, while all the groups makes up the entire sampling space. Next, we do the sampling inside each group, just as Monte Carlo sampling. Finally, we compute the confidence value for each vertex based on the sampling results. The intuition is that the stratified sampling process tries to balance the sample graphs. Another sampling alternative is lazy sampling. We find that in Monte Carlo sampling, in each sample graph, the algorithm must visit all the edges in the original uncertain graph to decide whether to keep the edges or not. In order to boost the query efficiency, the lazy sampling technique is designed to skip the user's edges. Specifically, in Monte Carlo sampling, we sample a real number between 0 and 1 for each edge. If the sample number is less than the edge probability, we keep the edge, otherwise not. On the contrary, lazy sampling samples an integer for each edge in the current sample graph, which usually has much fewer edges than the original uncertain graph. The sampled integer stands for in which sample graph this edge will exist next time. Therefore, until the loop goes to that sample graph, this edge is not needed to visit anymore. We perform experiments on 4 real-world uncertain graph datasets. They have various types, including social network, citation network, and PPI network. 3 of them are large graph datasets. We test the performance of each component in the pipeline, including the ICDE index, the pruning strategies, and the sampling techniques. 3 metrics are used in our experiments, that is the CPU time, the pruning rate, and the relative variance. The 4 figures above show that the ICDE index averagely gains 1.7 times of speed acceleration on 4 datasets. More importantly, the experimental results in the 4 figures below conclude that the pruning strategies make the pipeline executable for large graphs. Besides, further results demonstrate that the advanced sampling techniques can gain 2 times of speed acceleration and reduce 49% of relative variance. We also conduct a case study on the subgraph of DBLP, a well-known citation network, to examine the effectiveness of the proposed definition of k-theta community. The competitor is the k-theta core in the literature. We can observe that the k-theta communities are local structures around the query vertex, while the k-theta core in the right figure is more like a global structure. Besides, since the edge thickness is proportional to the edge probability, the results demonstrate that the proposed k-theta community exhibits the desired reliability when compared with other definitions. To conclude, in this work, we propose the novel k-theta community to model the community search problem on uncertain graphs. We present effective pruning strategies and sampling techniques to boost the query efficiency and reduce the sampling variance. We conduct extensive experiments on large real-world uncertain graphs. In the future, we intend to use parallel tools to further boost the efficiency. Thanks for your time. If you have any questions, feel free to contact me.